Welcome to BFO Practitioner Foundations. My name is John Beverly. I'll be your instructor for the 4-module series. I'm, as you see here, co-director of the National Center for Ontological Research. I'm an assistant professor at the University of Buffalo and affiliate faculty at the Institute of Artificial Intelligence and Data Science, and I am quite fond of and in favor of, and you might even say an expert in, the basic formal ontology, which is what I'll be teaching you about today through these lectures. So, as I said, Module 1, this is part of the Basic Formal Ontology Practitioner Certificate, which is part of the Foundation series from the National Center of Ontological Research. As you can see there at the top is the NCORE approved practitioner course, and the first module of it. This gives you a little bit of an overview of the 4 modules that comprise this BFO Practitioner Certificate. You'll see we'll discuss motivations for basic formal ontology, as well as the methodological convictions, the theory behind it, and then the logic of constructing basic formal ontology definitions. Today, for this module that is, I will just be talking about the motivations for basic formal ontology. We'll cover the subsequent modules in subsequent lectures. So, there is a massive amount of data out there in the world. I'm sure you know this. I'm sure it's not news to anybody listening. There's a lot of data and a lot of interpretations of data. And you see that second step over there to where you take the data, that raw input that comes in from sensors or your phone or the Internet of Things or whatnot, and there's a bit of interpretation, some semantics or meaning built into it. That is, roughly speaking, where we are right now in that information level, I think, with all the massive amounts of data that is coming in from all sorts of sources, and not just from our personal individual lives and our perspectives there when we're scrolling on the internet or something about our phone or with our phones, but like as we work in different institutions or agencies, we see the massive amount of information we have to pour through every day. It's very clear to see that where we are not is over here with knowledge, where we are connecting in a sort of streamlined or standardized manner, dots on the map, right? Like the connections between little data points here and little data points there. There's just too much of that for us to go through and sort through by hand. Manually. It requires too much expertise. What we really want to do is leverage, computer systems. Like they've been quite powerful in the past. Certainly could be leveraged here. I mean, it's not like we don't do these sorts of things. People leverage computer systems, computer architectures all the time, certainly to get from that data stage into the information stage, and in a piecemeal fashion from that information stage to the knowledge stage. But right now, our best efforts never get us past that knowledge stage and only gesture at it. And why? One of the major reasons that we can't get from information to knowledge more regularly is the existence of these information silos. What is that? An information silo it's a management system or database or knowledge base even, the content of which cannot be integrated with that of other information repositories using standard computing strategies. Now, you can probably understand this in terms of rather intuitive examples from your own life. I'm sure that at some point you have a friend who has had to store information about some topic in an Excel spreadsheet, or if not that, then you have encountered Excel spreadsheets where information maybe about you or things you care about were stored. Maybe if you work in some logistics capacity, you want to organize freight or inventory in a certain way, or perhaps if you work in the health industry, perhaps maybe you want to categorize or the results of various experiments or interventions that you've been investigating. So regardless, it is almost never the case that people working in the same domain organize that information in their respective Excel spreadsheets or respective databases or knowledge bases in the same way using the same standards. It is almost always the case, unfortunately, that, say, a researcher investigating cancer treatments in Michigan, say, and a researcher who is doing the same sort of work in California, at the end of the day, ultimately code whatever information they're gathering or have learned from their various experiments or investigations in different sorts of coding schemes, even if they're using like an Excel spreadsheet or a database or a knowledge base. They might talk about or characterize, say, specific types of cancer with different codes or specific types of treatments, even though they are the same across their respective investigations, they might code them differently, both syntactically and semantically. They might mean something slightly different, or at least use a label that suggests they do. The reason that this is important is because computers, or computing strategies, they are, in a sense, quite dumb. You have to be very explicit about meaning across different databases or across different systems or whatnot, because computers only know what you tell them, and they cannot sort out the subtleties of semantics that we tend to build in to these management or information repositories as we do. If I say, for example, that some individual owns an animal, then unless I make it very explicit and say that the animal is owned by that individual, the information system does not know. There's nothing it can say or infer about that. I have to make this information very explicit. I have to code it in a machine readable, or more robustly, a machine interpretable way. Again, lesson here is information silos block integration of data across data sets because of both syntax and semantics or semantic differences across these systems, and that gets in the way of computing strategies for integrating information, and that is what keeps us, at least has kept us for decades at this point, from going from information into that connected information or knowledge scenario, which I think we'd all like to get to. Now, I'm not making this up. This is widely known, this problem of information silos. In fact, in 2020, a report by NIST estimated the lack of interoperability, which again, a function of those information silos, across industrial data sets cost companies between $21 and $43 billion. That's billion with a B. And McKinsey estimated that mid-sized companies spend approximately 20 to 50 million annually due to such silos. So you see, exacerbating and exacerbated by these 5 V's of big data that folks often reference in this context. So things, observing just here, there's a huge amount of data in the world. It comes in a variety of formats. It's hard to extract useful information. There's inconsistencies throughout, and it comes in at a very high speed. Hard to get a handle on. Now, regardless of our strategies for attempting to address these 5 V's, information silos make them harder to address in almost every respect. Now, why am I talking about this, you might be asking? We're talking about basic formal ontology. You want to be a practitioner. You want to learn the foundations. Well, here they are. Ontologies and knowledge graphs, which are ontologies with data attached to them, are well-known solutions to information silo challenges. Now, ontologies, they are formally well-defined machine interpretable controlled vocabularies designed to represent entities and logical relationships among them. And what we do when we build them, that is we make explicit the implicit meanings that are buried in data sets, essentially by using basic principles of formal logic. It is important to highlight this aspect, the basic principles of formal logic that we use to make explicit, implicit meanings buried in data sets. Now, researchers will talk about their respective domains. Experts talk about their domains as they like. And none of us in ontology engineering circles are interested in telling experts how to talk about their domains. If you are an intelligence analyst and you want to use the word target in a way that is perhaps not in line with common sense uses of target, that is your prerogative, and you go right ahead. What we are interested in is not exactly the label, just the real meaning behind it. What exactly is the logical structure underwriting the way the term is used, and how does that connect up to the logical structures of other things in the world? Folks can talk how they like, but there's a fundamental logic that everything is based on, everything is grounded in, whether it's talking in or in natural language, whether it's talking in specialized jargon, or whether it's buried in data sets. And that is important because what we do is we uncover that basic logic that connects all data sets, and in doing so, we create a semantic layer that connects information silos, as I said. Researchers working in cancer in California, researchers working in the same types of cancer, investigating the same types of cancer in Michigan can talk as they like, can encode information as they like. They will, despite themselves, use the same logic. And what we do as ontology engineers is we make that logic explicit enough so that machines can reason over it. Now, I said, right, this is not exactly news, right? Interoperability, integration, and information silos have been around for a while. People have been aware of them. Now, as of the recent couple of years, ontology engineering and knowledge representation or knowledge graphs have really taken off. And so, as you can see here in the Artificial Intelligence Roadmap from 2024, the Department of Homeland Security is referencing data ontologies specifically in their work. As you see here on the bottom right, this is a report from Gartner in discussions of the future of generative AI, and you see knowledge graphs right in the center. Building the prototype Open Knowledge Network at the top from the National Science Foundation is a project that funded 18 different knowledge representation ontology/knowledge graph efforts to create artifacts covering a range of different fields like water supply management or industrial manufacturing, etc., at $1.5 million a pop. So a lot of money has been invested in this, in creating these sorts of architectures, again, in the interest of addressing interoperability challenges. And as you can see here, many nations in the world have been publishing quite a bit and more regularly, more rapidly in this area. And this is not new, this is from 2021, but if you search on Medium, which is where I got this snippet from, you'll see these sorts of posts all the time. People think it's quite easy to build a knowledge graph, quite easy to build an ontology, and in a sense it is. And you can use RDF-lib. It's a library of Python that allow you to transform whatever structure that a database is encoded in into something that ontologists are more familiar with, RDF being a resource description framework, which is our data model that we use. It's basically a triple format subject, predicate, object. You can use Python scripts to create such things without much difficulty. Now, if you're not careful, and most are not, what you end up doing though is just creating another information silo. Anybody can create an ontology or knowledge graph out of any given database. That is not the hard part. The hard part is aligning it to a standard. It is easy to build knowledge graphs, I will emphasize, but building according to a standard is hard. But that is how you avoid silos. Now, all of this is bring home to the point that basic formal ontology, what you are here to learn about, is the most widely used standard to avoid silos. And it has its origins in just that sort of activity. So back in the day, 1998, quite a few years ago, they started the Human Genome Project, where all these massive amounts of data were coming out about proteomes and genomes and like gene expression and protein expression. We're really kind of getting deep into the center of life, right? Well, it turns out there's quite a bit of data that was being uncovered. Massive amounts of data were being extracted daily, just increasing regularly about the human genome, mice genomes, like all sorts of genomes. And people recognized very early on that if they were not coordinating their research efforts, they would very quickly start talking past each other even when they're attempting not to, when they're trying to talk about metabolic processes, for instance, as you see here at the top. If researchers in Pennsylvania weren't using the same metabolic process in the same way that researchers in Florida were, they were going to engage in insubstantial disputes or just talking past one another, and they're not going to be able to integrate all this data. So it was recognized, again, early on, right as the human genome projects were taking off, or these various genome projects were taking off, that there was a need for this kind of integration. And so the gene ontology was created. The gene ontology is the mission of the consortium that ushered this in, was to develop a comprehensive computational model of biological systems that range from the molecular to the organism level across a multiplicity of species in the tree of life. And of course, covering all of this information was a major endeavor, and it's still going on. It's in fact perhaps the most successful ontology that exists. It has, I believe, since '98 received approximately $4 billion in funding. There's an open line at NIH where money is just thrown on to support it because it is used in so many different projects. Now, the successes of the gene ontology back then led to a proliferation of ontologies that were developed by various subject matter experts in nearby domains and computer scientists and logicians, all trying to explore the world, map out the terrain, create controlled vocabularies of this or that, like water specialty, physics, like statistics. Like people wanted to build models of everything, and that makes sense. Gene ontology was quite successful and has been, so they wanted to get on board and start modeling the world. However, almost none of these projects were developed in coordination with one another. And the result was a massive incompatibility of terms and relations, a lot of confusion, a lot of infighting, a lot of name calling, and ultimately a lot of information silos. So instead of the information silos in this case being at the level of data, like databases and management systems, in this case, ontologies were siloed from one another. The very same problem just emerged at a higher level. Now, around 2005, so about 7 years after the gene ontology kicked off, another consortium was founded. A biologist decided to create a standard for ontology development. It's called the Open Biological and Biomedical Ontologies Foundry. And among the many requirements they had were like that ontologies, for example, be open source or have documentation, include definitions. You can see the list here, and many of them are very important, and many of them have underwritten basic formal ontology and been underwritten by the basic formal ontology and linked very closely up with its success. So before, as a slight detour, it is worth discussing some of these as we make our way to BFO proper. So when I say open, what I mean is ontology, and this is from the OBO Foundry Principles, which you can look up right now. Or whenever you like, there's a link there. It is a live site. It's still going strong. The ontology, to meet this principle, must be openly available to be used by all, without any constraint other than its origin must be acknowledged, and it's not to be altered or subsequently redistributed in altered form under the original name or with the same identifiers. Essentially, this is a Creative Commons license, and that is required for any OBO Foundry ontology. Any ontology that is developed according to these open source standards has to meet or satisfy this constraint. In addition, they have to be represented in a common format that's made available in formal language that in an acceptable concrete syntax. The W3C, so the World Wide Web Consortium, has such a standard for ontology development. It's called OWL, or the Web Ontology Language, and that is the underlying formal language that any ontology engineering that you see in conformance with basic formal ontology will be conducted in. So OWL is the formal language we use. In other modules, I'll go in much more depth about the logical characteristics of OWL, what you can say and what you can't, but suffice to say for right now, to satisfy the constraints, again, these standards to help keep the field on the same path requires using a common format such as OWL, and again, it is also a W3C recommended standard, so it's not too hard or not too far-fetched if you think about it. So in addition, each ontology has to have a unique international resource identifier, and this is for terms, this is for relations, this is for like the logical connections between classes and instances in the ontology. And this is important because we want to be able to refer to the same entity multiple times. In the web, you can say anything about anything, right? And so what it was insisting, there was an insistence that we have unique identifiers for classes of terms like person or Rubik's Cube or computer. Like if you're going to create semantics or characterization about the logical structure of such things, then a unique identifier is going to be needed so that we can refer back to it, refer to it locally, refer to it globally. And IRI, as you see here, I have a bit of a diagram to illustrate a relationship to other RIs, or other Rs, I should say. It says International Resource Identifier, which includes within it URIs, URLs, URNs. So these international resource identifiers, of course, the broader class is essentially a string, a unique string that allows for ASCII symbols that covers a broad range of different vocabularies in the world. URIs, of course, are a subset of those. Those do not allow for the same number of ASCII symbols, which was a little problematic, a little too restrictive, especially if you wanted something like, say, ASCII in your identifier, or I'm sorry, if you wanted something like kanji in your, or kanji characters in your identifier. there was a need to have something broader, hence the International Resource Identifier. URL, of course, subset of URIs, and those are locators like you would see on the web. In fact, there's one right below called next to compare, that HTTPS. And then URNs are the named version of URLs. So versioning was the fourth requirement for the Open Biological and Biomedical Ontologies Foundry. And so in this case, ontology providers must have documented procedures for versioning their ontologies. And different versions of ontologies must be marked, stored, and officially released. And you can, I have a symbol here for GitHub. This is a very common place where these sorts of artifacts are versioned. But essentially what is required here is that folks wanted to see how ontologies were being developed, what the justification were for different decisions made or choice points made in the characterization of ontologies or logical relationships being developed, and they wanted to see how they matured over time. You kind of wanted to watch the practice, and this is not uncommon in basic software development, and so it was never a surprise that folks wanted to see, how the cake was made when developing ontologies. And it's something, again, many of us in ontology engineering circles adopt regularly. Our work is publicly available in open source versions, and you can see when they're released, when they're not, when we're working on them, etc. Also, ontologies within the Foundry must have a clearly specified scope, and the content that adheres to that scope, the scope is the domain that it is designed to cover. So this was important to make sure that folks did not create overlapping content. What had happened prior, again, in between that space when with the success of the gene ontology before the creation of the OBO Foundry, there were a lot of ontologies that were created, not coordinated with one another. They often overlapped in scope, and folks did not often say exactly what the scope of their ontology was, and so it became very easy on occasions for scopes to creep or shift around, like if you're getting pressed and saying, no, I'm creating an ontology for water management, and somebody else is creating an ontology for oceans or something, and maybe you press them to cede some of the content or cede some of that space because you're working on management systems and they're working on just the oceans, and they suddenly realize that they want to work on management systems too, and that was always in their scope. And so there you can see pretty easily how not defining a scope earlier on could lead very, very straightforwardly into these sorts of disputes that could have been avoided with a little more clarity. In addition, ontologies have to have textual definitions for at least the majority of their classes, and in particular the highest level terms. And so definitions are what help at least humans understand what classes or the vocabulary and the logical relationships among or class terms are about. So it was required that definitions be clear, at least just as described here. The majority of the classes have to have them, and for sure the ones at the very top. And why the ones at the very top? Why did they have to have them? Well, often if you're creating an ontology and you start at a very high level, you're going to introduce kind of broad categories of information. We'll see this in a moment with basic formal ontology. Some of that can be quite foreign to common sense, quite foreign to natural language, and so defining it at least gives users a handle on what the creator meant. And that allows them to work down from there and create textual definitions based on those top level terms. Also, collaboration was crucial. So ontology engineering should be carried out in a collaborative fashion. So as I said, one of the biggest problems was that these ontologies were developed after the success of the gene ontology without collaboration. They were not done in a coordinated fashion. And so one of the principles here is coordinate, collaborate. In addition, there has to be a locus of authority. Ontologies have to have some point of contact that's responsible for communications between the community and developers, as well as mediating discussions involving updates and ensuring feedback is addressed. One more time, this is about collaboration. There has to be somebody you can go to, somebody you can point to, somebody you can talk with more specifically about the development of the ontology changes, what might be addressed, and how, right? And again, this is all in the interest of making sure that folks work together as they build ontologies so they do not create ontology silos that just reinvent the information silos that they were designed to address. There's also the need for naming conventions so that there was at least some impulse so folks could have make it clear that whatever they were talking about in their vocabulary is actually linked up to the way scientists and machine learning or natural language processing could be used or understood. And so there was a requirement, and this is still true today, that there be primary labels for ontology elements that are understandable, not just like codes, strings of random characters, like GUIDs or something. Like, no, there has to be some human understandable label that the natural language processing algorithms can pick up on. They also have to be unique. At least in our circles, we pick the RDF colon label as the unique label that we use in-house for ontologist labels. And those often, the things we're labeling often look quite different from what scientists might talk about or want to see, but that's because we're ontologists and we have our own specific jargon. We'll see a bit of that as we proceed. But the takeaway here being simply that there are naming conventions, at least some minimal conventions. There has to be intelligible natural language expressions that are unique and used to pick out ontology elements. Now, I didn't go through all of these principles. I did go, I mean, many of them are relevant to basic formal ontology. Certainly the ones I just covered. Some of them are not, however, but all of them are important to understand the state of the field and how we got where we are today. Now, as I said, in 2005, the OBO Foundry was created with these standards and principles in mind. And in addition to ontology, or requiring that ontology be open source to have documentation, etc., was also required that they align to a top-level ontology which provided a starting point for all ontology development. Now, where to begin? OBO, Open Biological and Biomedical Ontologies Foundry, so natural place to start would be to look at Linnaean hierarchies, right? Shall we organize all of the data in OBO, all of the ontologies in OBO, according to such a hierarchy, like kingdoms, phylum, classes, orders, etc.? Does that really reflect a generalizable like structure, the basic logic that I pointed out? Or could we go back further and look at some very old structures, like metaphysical structures? I can't really even read these. Something like real thing, corporal thing, like rational thing, scientific thing, right? Irrational thing. Is this the sort of structure we should be looking for? It's closer perhaps to that basic logic than, you know, the domain specialization that you see in kingdom, phylum, class, but it's also a bit esoteric, and it's unclear exactly what's going on, not just because the image is fuzzy. Should we look at something of this source or this sort, maybe something a bit more Aristotelian, or surely metaphysical, like substances and immaterial, material things, or living things and non-living things, rational, irrational? Who knows? What should we go with? This was the question that many were exploring, and many trying to investigate. What sort of top-level structure should we adopt? There are many top-level structures. How do we decide? Well, fortunately, we don't have to, because what they decided on was to use the basic formal ontology, which is a standard, the top-level standard for OBO Foundry and many other Foundry efforts. It has, since that time, exploded in its breadth and at least usage. It's used now, at least right now, in 2024 on September 29th by over 700 open source groups. And it is the first ISO IEC top-level ontology standard, and it is considered a baseline standard for all DoD and IC formal ontology development. Now, in the history of ontology engineering, you see 2005 here, OBO Foundry created. Basic formal ontology was created alongside it. So while they did investigate and explore options like Linnaean hierarchies or traditional clades, and also various metaphysical ontology structures, they landed on a basic formal ontology and decided to adopt that. Now, a few years later, this web ontology language that I was mentioning, that formal way of characterizing ontologies in a machine-readable way, was introduced, and quite a bit of other activity emerged shortly after. As you can see, there was the development of Siri, which uses knowledge graphs even to this day, and then, of course, Google's knowledge graph. Recall, knowledge graphs are just ontologies with data attached to it. In fact, over here on your right, you see if you're searching in Google and you see the little a little box that pops up whenever you search a character or name or some noun. That little box popping up from Wikipedia, that is actually generated from Google's knowledge graph. Now, this is what we've been discussing, the Obo Foundry and basic formal ontology since way back in 2005. But as I said, many things have happened since then. Ontologies have kicked off in various circles. There have been waves of development. The Common Core ontologies was developed. Different foundry efforts were developed, Common Core being one of the better known extensions of basic formal ontology. Industrial Ontology Foundry, of course, being a foundry that took after the Obo Foundry and adopting basic formal ontology as the starting point. And then, of course, the basic formal ontology being an ISO standard 218382 in 2020, leading all the way up to now the 2024 DoD-IC Foundry using basic formal ontology as its top level. So it has grown. It has spread widely from its early days in 2005 with the Obo Foundry as its top level, and now we see it here in many other foundry efforts as international standards and a core for ontology development for large groups of individuals. As you can see here, as I mentioned a moment ago, is a baseline standard for the DoD and IC ontology formal development. Now, over 700 projects throughout basic formal ontology has created that ultimate high-level semantic structure on which other ontology efforts can be based and are based. And it's essentially, as I've mentioned, basic principles of logic that underwrite the structure of this formal architecture, which is why it's so widely used, why it's so, in my mind and experience, quite easy to use, and most importantly, why it's so effective at making explicit the implicit meanings across different sets of data, things ranging from, as you can see here on your screen, dengue fever, to space objects, to styles of delivery, to supply chain and bank ontologies, or autonomous driving-based systems. All of this uses the basic logic that you'll find and you'll see, and we will become quite familiar with as we explore in more detail the basic formal ontology. Now, to close out this module is, again, high-level overview of the motivations for and the breadth of basic formal ontology. I'd like you to follow this link here. Navigate to the module checkpoint page when you'll be asked a few questions about the content of this module. And with that, I hope to see you in Module 2, where we get into a little more depth discussing basic formal ontology proper.